Hi, it's Robin. Today I've got another interesting bug, this time in the input command on the VIC-20 and some Commodore 64s. So if you're not familiar with the input command, in its simplest form, you just input and name a variable, in this case a numeric version, and then we can just do something like printing out the input times itself, squaring it. So we'll run, a question mark prompt is displayed, and it's asking for the user's input, so we'll just say 5, that goes into variable A, and then it prints out A times A, 5 times 5, 25. Can also input a string variable, that's what the $sign means, and then we can print out something like hello, and then just print that string back at them again. At the user, run, there, hello, there. There's also a variation that allows you to prompt the user so they know better what you're asking for, like give me number, and then you add a semicolon after the constant string and the variable name again. If we run that, you see it shows the prompt, and then we can type it in like 6. Now, I didn't do anything with it, but if we print it out, print A, and you see that the value has been stored in A. Now here's the bug. If we just modify that program that just worked okay, and just change the prompt to something a little longer, like give me a bigger number. Okay, so exactly the same, but the prompt is longer. We'll run that, and then we'll try typing in something like 6 again, and we get a redo from start error. 5. Basically, it won't accept any input, or if we even type, a string like hello, no matter what, we just get this redo from start error. The only way out is if you hold down stop and tap restore, and that'll get you out for sure. Seems like a pretty bad bug. If we change that A into a string and run it, then we can give it a number like 5, and it seems fine with it. But here's the catch. If we print out what's in a string, see what's different here? It hasn't just printed the input we gave it, it printed out the whole prompt. Give me a bigger number, 5. Now if we run that again, and we can type a string or whatever, we print out that A string again, give me a bigger number, even includes that question mark that Commodore BASIC automatically includes with an input. So on the VIC-20, it's including the input prompt and the actual response from the user all in one string. And the reason it doesn't appear to work at all in a numeric variable is because when you run it and you type in, a number, it's actually passing that whole give me a bigger number 5 and try to put that in variable A, but because it expects a numeric value, that's not accepted, and this strange redo from start error just indicates that you gave it invalid data for the variable type. Okay, so I said that some C64s suffer from this. So let's try that. We'll come back to the VIC-20 later with an appearance from a special guest who knows a lot about plywood. Okay, so I've got here a breadbin Commodore 64, and this is an older one that has kernel version 2. Excuse that the video output of this isn't as nice as some of my other computers. So at first glance, it might look like this does not suffer from the bug, because if we run this, give me a bigger number and press 5, it just returns ready. It works fine. But this is when we start figuring out a bit more about the circumstances for the bug. If we just make this prompt longer, I'm not being imaginative here, I'm just going to extend it with a bunch of spaces and make it a whole line long. Now the prompt is 40 characters. And we'll run that. Give me a bigger number. You see that the question mark prompt has wrapped around to the next line. There, now we're getting the redo from start. So the bug has to do with when the input prompt causes the question mark prompt to wrap around to the next line. That's a lot easier on the VIC-20 with its little 22-column screen. On the Commodore 64, you need to hit the 40 character mark before it wraps to the next line. Okay, so I've got my Commodore 64C here, and the bug is fixed on this one. So if we just do input, give me a bigger number, and if we pad it out to 40 characters and run that, we'll see that it works just fine. We'll even make it that long. Way out there. So I did a whole video about the kernel revisions, but just so you know how to identify what kernel version you have, here's an Easy Flash 3. This has a neat feature to replace your current kernel. Kernel version 1 is actually quite rare, and it seems since the last time I used it, my Silver Label Breadbin 64 is in need of repair again. So instead, what I'm going to do is demonstrate kernel version 1. I've got it installed on my Easy Flash 3, top left corner, C64 kernel version 1. I'm going to press number 1. So this is still 64C with the newer VIC chip and SID and so on, but it's now running the old kernel operating system. So two easy ways to tell. If you want to test this for yourself on your Commodore 64, poke 1024,1, and that will put a white A up in the top left corner. And if we print peak 65408, this is called the kernel version byte. It returns 170. Now, back in kernel version 1, I don't think they intended this to be a kernel version byte. Well, maybe they did. That number 170 is kind of odd, but in hex that is AA, and in binary that is 10101010, which is a common pattern for unfilled memory. So I think it was just a spare byte that was just like basically undefined in the original kernel. And back here on the kernel version 2 breadbin, if we poke 1024,1, you'll see that the A does not appear in the top left corner at all. Well, it is there, and you can see it when the cursor flashes on it, but it's invisible otherwise. It's printed in the same color as the background. So that's characteristic of kernel version 2, and that led to all kinds of bugs in programs where pokes did not appear on the screen unless they were accompanied with a poke to the background color. And if we print that kernel identification byte, print peak 65408, then it returns 0. Okay, and back to my 64C with no cartridge, just using the stock kernel version 3 that it came with. So one more time, we'll poke 1024,1, and for the third variation, we'll see that the top left corner is printed in light blue, the same as the text color. So those three variations, kernel version 1 will print the A in white. Kernel version 2, it'll be invisible because it's actually dark blue. And here in kernel version 3, light blue. And to print that kernel version byte, this is finally a sensible number. It returns 3. Kernel version 1 is 170. Version 2 is 0, and version 3 finally returns 3. Those are the main variations for the Commodore 64. There were other variations. Check out my thorough video on that topic, which I'll link to. Okay, back to my breadbin, and this time with the Super Snapshot cartridge. Okay, so let's do a walkthrough of the bug. So I've got my Super Snapshot installed, and we're going to use the machine language monitor. I've never seen anybody do a real write-up of how this bug is triggered. So this actually took me hours of research, going through hundreds and hundreds of lines of ROM code. So we're only going to look at the narrow little bit exactly where this bug happens in kernel version 2, just to try and keep it on topic. This would be really sprawling otherwise. I'll show little inserts from the book Mapping the Commodore 64. So just pause the video and read those inserts if you want to learn a little bit more about what some of these system variables do. Okay, so we're in the code inspector and super snapshot, the machine language monitor. When input is called, then this code at F157 is called. Let's look at this here. So we'll see many zero-page locations that both BASIC and the kernel have reserved. So this 99 hex is where the input is coming from. Could be the screen, the keyboard, maybe others. But if it is from the keyboard, device 0, then two system variables are kind of backed up, so to speak. D3 is where the current cursor column, or X, is. The logical cursor column, and as you may know, Commodore 64 and VIC-20, with their shorter line length, you can actually combine multiple physical lines into one logical line. So the Commodore 64 can combine two physical 40-column lines into one 80-column logical line, and the VIC-20 can combine four 22-column physical lines into one 88-column logical line. So even though this is the column position, or the X, across the screen, it's not limited to 0 to 39. It's actually from 0 to 79 on the Commodore 64. And that's stored in the system variable CA, which tracks where the input started on the screen, X. And then this is the row, or Y, and that's in D6, the current cursor position, and that's stored in C9. So input needs to store these variables because unlike some other computers that were just command line based or line based, Commodore computers have a full screen editor, and that means that when you're doing an input, it needs to know particularly what line on the screen. The user is actually free to move around. So we've stored the starting X and Y position of the cursor for an input, and then the system jumps away to this E632, which is actually the screen editor that's active, like even right at this very moment while we're scrolling around, and when you're coding in BASIC. So if we look at that, that's actually gets really complicated. But the important thing to know is that all this code is constantly running whenever you've got free control of the cursor in BASIC or whatever. And what it's really waiting for is for you to press return. So we'll look at that. That's at E5FE. Okay, so there's a compare 0D, and that's the code for return or carriage return. So once that's been pressed, Y is loaded with D5, which mapping says is the maximum length of a physical line, but I think it's actually the length of the logical line. So on the C64, that would either be decimal 39 or 79. And then a little scan is done. D1 should always point to the beginning of the current logical line on the screen. So it could be extended up to 79 characters, up to the end of the second physical line, the end of the 80-column logical line, and it'll scan backwards, looking for the first non-blank character, and Y is decremented each time as it scans backwards, and either if the whole line is blank, or once it finds it, and it stores in C8 the end of the input. So that should be, I think, between 1 and 80. And this is a crucial part. D3, which is the cursor column position, is reset to 0, to the beginning of the line. And then X is loaded with the current cursor row, or the Y position of it. And then this routine here, E6ED, is called. And this is essentially the bug right here, or this is why the bug happens. So if we just look at that routine, and it's just a short routine. You remember X is loaded with the current row, and it looks in this table called the line link table, starting at D9. And this is on the C64, 25 0-page bytes, each one representing a row on the screen from top to bottom. And the high bit is set if this is the start of a logical line. So at first, all 25, again, I'm just talking about the 64, it's a little bit different on the VIC-20 because of the different numbers, but all the logic is exactly the same. It starts off with the high bit set on every one of these because every row starts off as a 40-column logical line matching the 40-column physical line. But when you start typing or printing beyond the end of a physical line, then the next physical line is linked with the previous one into one 80-column logical line. And that happens by the high bit being cleared, set to 0, for that second line. So what this does is just does a little rewind. Whatever the current row is, it checks, is that a primary, or like, is that the beginning of a line? If not, decrement X, go up one line, and then branch and check again the previous line and see if the high bit is set. Now on the C64, because you can only link 2 lines, this almost seems redundant because there's this little like loop, but really it's only going to either be the current line or the previous line that's going to step back to. But on the VIC-20, because you can link up to 4 logical lines, it might actually step up, up to 3 backwards with this loop. So what happens here, X is rewound to the physical line that starts the current logical line. And this is the bug because this makes a wrong assumption. So after that rewind, it jumps to E9, F0. And this is just a short routine that uses that X row. I know it's confusing. It's using X to mean the row, but that's very common in 6502 because X and Y, the way the registers are set up, are kind of non-orthogonal. I almost wish they had reversed them, but that's about 50 years too late. So what it does is it looks up in this table. This is a screen address table, and so it just looks up the low byte and then calculates the high byte for that D1, D2, which is the pointer to the screen address of the beginning of the line. It just does that in case it changed, in case it did rewind. Now D1, D2 should be pointing to the beginning of the line, and that's fine. And then it does a return. Okay, now to rewind back to where we were. Okay, so this is the call that was made here, and the damage has been done. So the current cursor row at D6 and the starting input row are compared, but because of this routine, in this circumstance, D6 is being decremented by this routine, so they no longer match, even though they should, because calling this routine assumes that the input was starting on the first physical line, even though that's not necessarily true. I know this is confusing. This took me hours and hours to figure out, so I hope I can explain it well enough. If I clear a few lines at the top here, input prompt, blah, 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 do this example, and there's our input prompt, and this is where I would type in hello, for example. Okay, so this is row 0, this is row 1. After printing that long prompt, both D6 and C9, current row and the start of the input row, are both 1. But then when E6ED is called, that rewind function, it scans back for the start of the logical line, which is here, and changes D6 to 0. So because those are no longer equal, the current cursor position has been set to 0 up above. So our input should be told that we're starting at column 43 or 42 or whatever. Excuse if I'm off by 1. It doesn't really matter for understanding this. But it's being reset to 0 to here. And had D6 and C9 still been equal, as they should, then here D3 would be restored from the input position here, we'll go back in the cursor position, and then the input would be read starting from the correct position, like here, for example. But because these are no longer equal, now the input is considered to be starting right at logical line position 0, and therefore all this is now considered the input. Okay, so that's the bug. Okay, so how is this fixed? Well, let's start by just looking here on my 64C, now again with the Super Snapshot installed. And if we look at that same bit of code, just scroll down a bit here, it's all exactly the same in this area, except that JSR E6ED has been changed to E591. Okay, and what is that? E591. It's just a tiny little bit of code here, a little patch actually, and all it does is it compares X, the current row, against C9, importantly, before E6ED is called. And if the current row is the same as the input row, then it will branch over and not call that routine that scans backwards, that rewind as I've been calling it. So this is just acknowledging that it's possible that we did not start the input on the first physical line of a logical line. And that's really all there is to the patch, just doing this check before and skipping the rewind feature, and then it just continues on its way. And you see, just to make the patch work, they even added a little NOP here just to fill that extra missing byte. So the patch is very simple, but fitting the patch in wasn't so simple. So because that's hard to show on the real thing, I want to do a comparison. We'll go over to my modern computer where I've lined up the two and we can look at it there. Okay, here we are at my modern computer. I don't really like doing this, but I couldn't think of a better way of showing how C64 kernel version 2 and version 3 differ. Now, this isn't the only difference between the two ROMs, but that's what we're looking at today in regards to this input fix. So I've lined them up. So kernel version 2 is on the left, kernel version 3 is on the right. You can see that the differences start at E5-7C in both cases. Kernel version 2 had this routine here. I showed how the high bit of the line link table indicates if that corresponding physical line is the start of a logical line, but it's also used to calculate the screen address for that pointer we talked about at D1, D2, a 16-bit pointer to the screen address of the beginning of the logical line. So normally that was calculated here, but this code's actually redundant. So what kernel version 3 has done is issued a single call here to JSR E9F0, and that's actually really similar code, which I pasted in here. I've indented it just to show that's what it calls. That's not actually in this memory location. And you can see this code very closely matches the code over here on the left, but this was pre-existing code. Really, the only reason they've done this is so now these 3 bytes, this single JSR call, replaces all these bytes here on the left, just to make room for the patch. So you see a lot of the changes aren't really about the fix itself, they're just to make room for it. Okay, now the next section is exactly the same, where the current line length is being calculated, and we don't have to get into the details of that, but basically it calculates on the C64, is the line length either 39 decimal, which is 27 hex, or it'll add 28 hex, which is 40 decimal, to calculate the length of the logical line, and stores that in D5, which I said I think mapping the C64 is an error where it says physical line. It's actually the logical line. Now this all seems over-engineered here, but it's because the VIC-20 uses very similar code, but it makes more sense there because 4 physical lines can be combined into one logical line. So all this kind of starting with the base value and then adding the line length makes a lot more sense. This actually could have been shrunk even more, I think, on the 64, but they didn't bother. But the important thing here is that you notice that in kernel version 2, this starts at E5-8A, but in kernel version 3, because they've replaced all this code with a single JSR call, this calculate current line length section can start at E5-7F, about 10 bytes earlier than on this side. I put them side by side so you can show they're the same code. This is actually earlier in memory. And then while the original just returns, over here, there's a jump to EA24, and this is an unrelated bug fix that they've squeezed in here. And I think this is actually the fix for that lockup bug in kernel version 2 that I showed in that long kernel video before. And again, I've indented the code it calls just for reference. It's not actually in this section of memory. It's off at EA24. So they used up a couple more bytes instead of the return. They've got a jump here. Okay, and finally, all that just to make room for the fix for the input bug, which we already went over. And just to make things line up for the patch, right where that return used to be at the end of that memory block at E599, now there's a NOP there. You can think of a better use for it, go for it. Okay, and that's not the whole fix. The other related part of the patch is down here at E621. Originally, that rewind function, or I was calling it the find first row function, was called every time. Instead, the new fix just replaces that address with E591, which is our patch right here. So here's the fix, but it has to be patched in here, and that's it. Okay, so that's the difference between kernel version 2 and kernel version 3. So this was never fixed on the VIC-20, and as we see, it existed in the first 2 versions of the C64 kernel even. So it made me wonder, would it be possible to apply the input bug fix back to the VIC-20? So to figure that out, I went looking through the C64 kernel version 2 and the VIC-20 kernel. So the bug exists in kernel version 2 C64 and the VIC-20 kernel, and I found where that code lines up pretty much perfectly. On C64, it's at E5-7C, and on the VIC-20, it's at E5-9-7. But if you compare them, you see the line link table's in exactly the same place. The whole D1, D2 calculation is identical here. Really, the only difference is that the 27 hex, which is 39 decimal, on the VIC-20, 15 hex, which is 21 decimal. This is one less than the row length on the C64, and this is one less than the 22 columns across the VIC-20 screen. Okay, and then all this code's the same. Of course, the branch is different, just because the VIC-20 ROM, while sharing lots of code, ends up being assembled to different locations in memory just because of the differences. As we're building up that logical line length, the C64 version adds 40 or 28 hex, while the VIC-20 version adds 16 hex or 22 decimal. But ultimately, it's calculated and put in location D5 on both. And they also located where that rewind function is and where it's called is here at E63C, and it actually calls E719, again offset a bit, but it is the same routine. So once I isolated that in the VIC-20, then I lined it up against the C64 kernel version 3. And you can see there's lots of differences here, but now we can just kind of do a comparison and adapt kernel version 3 to match the VIC-20 layout. So that's what I've done here, where basically I've taken kernel version 3 and looked up where it called this E9F0, which is that pointer fix routine. I located that in the VIC-20 at EA7E. And whenever we see a 27, that's 39 decimal, we just change that over to 15 hex or 21 decimal. This code maps exactly the same. Whenever there was a branch, if it was a branch inside the code, then we just had to keep the same offset. So for example, this branch minus branches ahead on the 64 from E584 to E58C. But if you look at the hex representation of it here, the branch of minus branches ahead 6 bytes. Well, you just keep that exactly the same on the VIC-20. 28 hex 40 decimal gets changed into a 16 hex 22. And again, the branches just keep the offset the same here. 10 F6, same over here. This jump to fix the color RAM, I found the equivalent of the VIC-20, it was EAB2, and so on. I think these are all basically the same. And that rewind function is here at E719, and then the return, the NOP, and here E621. The JSR E591 changes into JSR E5AC, just the equivalent routine on the VIC-20. And you can see here just how it compares with the original. Kind of borrowing some of this, and coming up with a VIC-20 fix. And here I just wrote up the patch. If we take the 8 kilobyte VIC-20 kernel binary, there are 30 bytes that have to change at offset 597 right here. And there are 2 bytes that have to change just to fix that JSR to patch it in. And I just used a hex editor to make those changes. And you can too. I'll put these bytes in the video description if you want to copy and paste them for yourself. This kernel is still under copyright and it's being used in products like the C64 and the VIC-20. But here's the patch and you can do it yourself. I'm sure somebody will make it available publicly. So now that I've made that patch, I'd like to test this on a real VIC-20, but I don't have the means. Nobody's invented an easy flash type cartridge to replace the kernel. I don't currently have the EEPROM adapter I'd need to actually replace the kernel physically in my VIC. But fortunately, resident plywood expert and EEPROM emulator owner, Mr. Doornbos, does have what it takes to test the patch on a real VIC-20. So let's go over to him to show the before and after.
All right, Robin asked me to demonstrate this bug or the bug fix on a real VIC-20. I've got my EEPROM emulator here so that we can swap the ROMs in and out really quickly on the VIC-20. The ROM in question here is the kernel ROM. So on a CR board like this one, you have the processor, you have the kernel ROM, the basic ROM, and this one's the character ROM. If you have a older or 2-prong board with the power supply or the power regulator on the board, it's UE12. They're both UE12 actually. We have kernel ROM, basic ROM, processor, and then the character ROM is here on this board. Kind of assume that you don't have one of these EEPROM emulators. If you do, great, then they work really well. But there is a modern solution for replacing the ROMs on your VIC-20 or Commodore 64, actually any of the 8-bits, by a site called DIY Chris. This is a drop-in replacement for 2364s, and if you pull this jumper off, then it turns into a 2332. So let's get this set up and get the bug loaded. All right, I've got the EEPROM programmer kind of gently inside underneath this the keyboard here, just gently set on top of it. We've got our input prompt loaded. This is the default kernel, and if we run it and we enter a prompt and then we print A, we can see that we get not only test, which was part of the input prompt, but we get the prompt itself, which is the bug. So now we're going to switch over. Now, if I quickly swap out the ROM image, this should be with the bug fix. And now, if we run this again, although I'll actually spell it correctly, and we print our A string, the bug is fixed. That's it. Back to you, Robin.
Okay, thanks very much, Michael. That EEPROM emulator is really great. I gotta look into getting one of those. And to all you viewers, I highly recommend Michael's blog, IamThePenguin.com. There'll be a link in the video description. He's written many great articles about retro programming and more, so please check him out. Thanks very much to my patrons for their support and patience while making this kind of extra involved video. Thank you for watching, and we'll talk to you next time.